Hello, hi everyone. Yeah, hi. Um, yeah, hi. How are you all? Shweta. That's right. I already shared the recorded sessions, and also some of you attended for the last three demo sessions, right? So today we are going to start with a system verilog. Actually, yesterday only I need to start, but due to some network issue, I am not able to start yesterday. Right. So I think everyone know Verilog HDL. How many of you have don't have any idea in Verilog? I think everyone know Verilog, right? Properly, how to write the test benches, how to write the design, and what are the test bench constructs like simulator directives or system task, how to initiate the DUT, everything clear, right? Verilog batch, Sunny,
Yes, ma'am, clear.
any pending sessions?
Nope.
No. Okay. Okay, fine. But in Verilog HDL, we left with two topics. So one is P4 memory and finite state mission. We already discussed, but we need to discuss few more examples on FSM. We will cover these two things parallelly. Whenever we get time, one day I will complete these two also in Verilog. Other than that, everything is clear, right? In Verilog. So, what are the limitations of Verilog? We are going to start with that. Already we discussed the limitations of Verilog. Mostly Verilog is static in nature. We use a module, right? So everything we write in the module. So module, name of the test bench. Inside that we need to declare what are the inputs, what are the outputs, and we need to instantiate the DUT. That means test bench and DUT we need to interconnect. So we will discuss the limitations and purpose of verification. Today we are going to discuss what is the purpose of verification, how to verify a design, and the system Verilog overview, like how we have written the test bench in Verilog HDL and how we are going to write the test bench in system Verilog. And tomorrow, I mean, in the next session, we are going to discuss with the data types. We'll start with the data types, arrays, operators, and the test bench components. Today we will discuss. And in system Verilog, we have different types of arrays like static array, dynamic array, associative array, queues, task, function. So regularly few topics every day, two topics we can discuss. We need to cover both practically, right? Not only just a simple explanation in theory. Everything we need to write in a practical programming wise. So we need to connect every example with a real time how we use in industry. Okay, so in now only I'm telling. So whatever you are learning, the assignments, whatever we are giving the assignment, try to learn everything in depth. Okay, just don't go through basic. Okay, our course mainly in a Probi logic, you are not going to learn just a basic. Okay, you are not going to learn only definitions like that. Okay, everything we will give clear concept in terms of industry oriented. Every concept we are going to apply practically, even data types, arrays, functions, queues, these things also. Okay, so whenever you are learning, you need to follow same. Okay, just don't learn like a basic understanding of like a definitions like that. Okay, try to program. Whenever you are writing some piece of code by yourself, then only you will get lot of errors. You can able to debug the errors, you can solve more number of logical questions. Okay, so mostly from day one onwards, we need to write the program. We just not learning the theory. Okay, so everything everyone be like focus on that thing. Okay, try to write the program. And also we are going to discuss interface, virtual interface, verification features, clocking blocks, mode ports. These all are every feature, every small topic also important. Okay, we cannot skip any of the topic. Every minor topic is most important. Suppose here interface is there, what is the main use of interface? Suppose in Verilog HDL, we interface the DUT with the test bench, right? We just write a single line in Verilog. But in system Verilog, we write a separate file. Interface is a separate block, okay? And also in that, there are clocking block mode ports. Why? Because for more synchronization between test bench and the DUT. But in Verilog, we don't have this concept. In system Verilog, every concept is a very complex. We need to write lots of code. Okay. But once you know how to write the program, for every design, whatever the design you consider, we will write in a same way. Okay. Same structure, same way. But according to the functionality, we will change some logical coding. Okay, sometimes we need to write a simple logic, sometimes we need to write a more piece of code. Okay, sometimes we need to include some coverage reports or scoreboard. Just how we write different ways, that's it. But structure wise, same. Okay, it's not like a C language or Java. C language or Java, whatever you write something, we need to learn every day something newly. We need to create new logics every day, right? But in system Verilog, once you know how to write the test bench architecture, for every design it is a similar. Okay, but whenever you are practicing more, you can create lot of ways how you can implement a simple way of writing the program. That is very important, right? Whenever you practice more, you can able to create lot of methods how simply you can connect overall path, because here everything we write in a object oriented program. Object oriented programming means what? We connect everything in a real time class based verification, which is a dynamic in nature. It's not static in nature. Verilog is a static in nature, right? Static means everything fixed. We cannot change every time in a runtime. We cannot change. But dynamic means whenever some error is getting, immediately we can change that, and it will be updated in the runtime. So there are a lot of good features in system Verilog. Okay, so we will learn one by one slowly. Next, one of the major topic in system Verilog is object oriented program, like how we create the class. Whatever the program we are writing in system Verilog, everything we write within the class only. Okay, class, something, class name, end class, middle, functionality. Like that object is nothing but the instance of class is nothing but object. Okay, and also most confusion topics: polymorphism, inheritance, encapsulation, virtual abstract class. All these are most confusion topics, but whenever you are practicing, you must have clarity on each topic. We need to link with the real time examples, and we need to practice. Okay, so whenever you practice more number of times, then we'll get more exposure, and also we are able to create the good logical way. Okay, and randomization, you already know what is meant by randomization. In Verilog HDL, we already use this concept, but that is very basic thing with lot of limitations. Okay, but in system Verilog, we don't have lot of limitations. We can able to control the randomization, but in Verilog, controllability is not possible. Okay, like that coverage is also one of the most important topic in system Verilog. Not only in system Verilog, in verification, coverage is one of the most important thing. Okay, why? Because suppose, am I audible?
Yes, yes, yes.
Yes,
Suppose
ma'am.
there is a SOC, system on chip design. Okay, in system on chip design or whatever the IP design. Okay, in IP design there will be multiple number of blocks. Okay, multiple number of functional blocks, whatever it is related to the memory or it's related to the protocol. Okay, whatever, there will be multiple number of blocks. So here we write some piece of code, and here also we write some piece of code. I think in the first session, second session, I explained the coverage very clearly. Whenever you want to verify some functionality, whether we have verified that particular functionality or not, 100%. Okay, when verification engineer task will be completed, whenever the coverage report is getting 100%, that means overall functionality, whatever the RTL design engineers done some RTL design, we need to check every functionality is working correctly or not, whether it is verified properly or not. That means what? We will verify the functionality, that is okay. But every functionality, suppose memory is there. In a memory, there will be address. Address will be 32-bit size, suppose. And there will be a data. And data will be 32-bit size. Okay. In this 32-bit size, if you verify the functionality, that's okay. Okay. But in the 32-bit size, how many number of scenarios will be there? 2 power 32 number of scenarios will be there. Whenever you verify all 2 power 32 number of scenarios, that's what 100% coverage. Even if you don't verify one particular scenario, we don't get 100% coverage. Okay, that's what we need to check in the functional verification. That's what functional coverage, toggle coverage, and cross coverage, code coverage. There are different types of coverages. Okay, we are going to see those coverage clearly. And yeah, this is what functional toggle. And most important topic, another one, assertion based. If you are fresher, you can avoid this, but if you are experienced, you need to learn deep into the assertion based verification. Just validating the behavior of a design. Suppose before I told verifying the functionality of a design, and there is a much difference between verifying the functionality of a design and validating the behavior of a design. Okay, suppose here I told 2 power 32 number of cases we need to verify. That's what we call as a coverage. Okay, but validating the behavior means what? Suppose at particular positive edge of the clock, address value is something and data value is something, whether both are correct or wrong at this particular edge of the clock or particular address. Okay, whether both are meeting the specification or not. That's what validating the behavior of a design. Okay, coverage we do for verification. Validating for a behavior means it's an assertion. Okay, we have different types of assertions like immediate assertions, concurrent assertions. Those things we'll discuss more detailing. And next thing is direct programming interface. It's not much required, but we will discuss the conceptual wise. Okay, that means suppose in not only in system Verilog, we can write the program, the verification of hardware description language using C language also, C or C++. Okay, but when you write the test bench using C or C++, how we are going to interface that C language with the test bench? Okay, so we are going to interface by using direct programming interface. That's what DPI. Next, inter-process synchronization, and these topics are most important. Test bench components. Whatever the test bench we are creating, every component you must need to understand, and every component we need to design properly. Okay, so coding wise, you need to follow the syntaxes. Whenever you practice regularly, then only you can write particular syntax without copying, without taking the reference from any other code. You can write your own syntax. Okay, and test bench examples. We will see a lot of examples how to design the test cases and test plan. In industry, if you are a verification engineer, first of all, if you are planning to verify something, some design, some IP block or any functionality, then first of all, you need to have a test plan. What is meant by test plan? Test plan is nothing but it have n number of test cases, why that particular test case is used, and what functionality it is going to cover. What functionality we are going to verify using the test case. That's what the test plan. And the details of the test cases will be there, like test ID number, or which suit it is related, or which functional block it is related. with just a test ID, like suppose your name is there. Suppose if you enrolled in this course, you're you're having some data, right? Your mail ID, like contact number or name, what is the course name. In the same way, test plan is nothing but the details of the test bench. Okay. And also, whenever we run the test bench, whenever we do the simulation, we'll get the errors, or sometimes the test case will be passed, test case will be failed. So everything will be updated in the test plan. It's just an Excel sheet where we have some data. And test cases, in the sense, suppose here I told 2 power 32 number of test cases we need to verify. Okay, we can call it as a test cases or test scenarios. The combination of test scenarios we can put under one test case. Suppose here 32, 2 power 32 number of scenarios are there. All these 2 power 32 number of scenarios we don't put in a one test case. Suppose commonly we are in one test case we are doing the randomization between 100 to 200 scenarios. In second test case we are randomizing 500 to 1000 scenarios, like that. Okay, so we'll have multiple number of test cases, and there will be regular assignments, mock tests, interview preparation. Everything will be parallelly. Okay, we don't have separate theory sessions, separate lab sessions, like that. Okay, everything in a same, like topic wise, both theory and the lab will be done at same time, just topic wise. Okay, clear till here? Any doubts?
No, I'm fine.
No doubts? Okay. Okay. So what is meant by verification first of all? What is the need of verification? Can anyone tell? What are the different types of verifications are there? Suppose if you are applying for a verification engineer, what role you will prefer mostly? Fast.
Functional verification.
Functional verification, okay.
IP verification.
Okay, what is mean by IP verification, functional verification? What is the difference?
Ma'am, in functional verification, we verify the functionality and we check for the specification. We write the test code according to the specification. Or in IP verification, we write the test bench for a whole means for a small block like that. For verifying a small block like that.
Okay, fine. Okay. So first of all, what is the need of verification? You already know verification is a critical step in a semiconductor design flow. Verification is a separate field, design and verification. So once design is done, RTL design, we cannot send directly the design to the backend process without doing verification, because we don't know whether we have the connection issues or functionality issues, whether the output is getting correct or wrong, anything we don't know, right? For that purpose we need to verify the design. Whatever the functionality is there, for the functionality we are creating number of test benches or test cases and we are trying to verify. Okay, so as a verification engineer, our main task is to verify a whole design, a whole system. So whole system in the sense, nowadays we are not using mostly ASIC chips or FPGA, right? FPGA are used, but for those applications are separate. If we talk about the processor related, mostly we use a system on chip design. I already discussed about the system on chip design, right? What are the different functional blocks are available in SoC? There will be n number of cores, processors, and graphic processor, digital signal processor, memory blocks, IO peripherals, Bluetooth, Wi-Fi module, GSM module, keyboard. There are a lot of interconnects also. Suppose here processor need to connect like this. These blocks will be connected through interconnects. This is overall system on chip design. Okay, system on chip design means whole architecture will be placed in a one chip. Okay, so you need to verify this whole system on chip, right? At some point of time, suppose first we will verify individual blocks. What we call these individual blocks, like a subsystem. Suppose memory subsystem, this block is related to the memory subsystem. In memory subsystem, what will be there? IPs will be there, right? Different types of IPs, IP1, IP2, IP3, IP4. Suppose this IP is related to the DDR memory. This IP is related to the RAM module. This IP is related to the DMA controller. Like that, one memory subsystem have different types of IPs, intellectual properties, or VIPs. VIP or like mostly protocols we call as a VIP. So here in this block, in this subsystem, there are two different IPs. One IP is related to the Wi-Fi module, second IP is related to the GSM module. Suppose so processor have the n number of cores. So first of all, whenever we are doing the verification, we need to come from low level. Okay, so inside first we need to verify the IP. All functionality is working properly, everything is verified, then subsystem level we need to connect, and then SoC level we need to connect. Okay, so I think everyone understood what is the difference between IP level verification and SoC level verification, right? And we will have the formal verification, functional verification also. Functional verification means what? Till now whatever we discussed through the coverage, we do the verification of actual functionality. Okay, formal functionality means validating the behavior using assertion based verification. Mostly in a formal verification we write assertion based verification. Okay, mostly assertions we write, coverage and assertions, because it's a whole formal verification means everything is validating the behavior. Every functionality is checking with respect to the design behavior. Okay, so like that we have pre-silicon verification, post-silicon verification. Pre-silicon means what? Before dumping into the hardware, into the silicon, whatever the blueprint is there, RTL design, if you do the verification for that, it's a pre-silicon verification. Post-silicon verification means after dumping into the chip. Okay, the chip hardware is ready. Suppose this hardware is ready. It's a system on chip design, hardware, not software. So this hardware also we need to do the verification, because we don't know whether we dump properly or not. After dumping, whether the functionality errors are there, or any miscommunication or connection issues will be there. Okay, everything we need to check. So to check that, in a hardware level, in a post silicon verification, we have separate team called DFD, design for debug team. Okay, so we will connect these system on chip blocks to the debug units. Suppose this SoC processor is connected to one debug unit, and here this processor is connected to one debug unit, and here it is connected to one debug unit, and this block is connected to one debug unit, and here it is connected to one debug unit. So why we are connecting all these things using to the debug unit using cross trigger network? We will discuss these things more detailedly in the last, at the end of the course in a system on chip design and verification. We discuss these things. Okay, so we will connect all these blocks to the debug unit. Here we trace the debug data or whatever, whether the tests are passed or failed, whether the test functionality is passed or failed, whatever, we will trace all the data here in the debug unit. Okay, in here we will write n number of test cases. There will be test cases already in the pre-silicon verification. There will be n number of test cases, right? whole test cases we will connect with the debug units. Okay. And these debug units are connected to the hardware because it's a hardware. Okay, it's just a suppose FPGA block. You know the FPGA, right? Arduino boards or FPGA boards. It's just a board. So this board we are going to verify. So how you will get this information? Whatever the board is connected here, you need to understand the internal signals of each functional block, right? So where you will get internal signals of each functional block. Suppose here there is a router connection or there is a memory connection. For memory, how many signals will be there? There will be a clock, reset, address, data. If you are taking FIFO memory, it have some control signals like empty, write pointer, read pointer, full. There are a lot of signals, but in SOC level there will be lakhs of signals. Every signal you need to verify properly with respect to the test benches, right? So how you are going to verify these things means we need to connect these hardware, whatever the SOC hardware is there, we need to connect with some tool, some software tool. Suppose your laptop, in the laptop whatever the software is there, based on the industry which company you are working, they have their own tools, right? So in that server we will get exact information what you need to verify. Okay, so that is what post silicon. So the entire hardware we will connect into the some tool. On that we will check every functional line to line, then mean every functional test cases, each test scenarios we will check. Okay, it's totally huge thing as of now, not required. Okay, I'm just telling what is meant by pre-silicon and post-silicon. Pre-silicon means whatever the blueprint we got, the specification wise we do the verification. Post-silicon in the sense hardware level we do the verification. Okay, clear everyone till here? What is mean by IP verification, RTL verification, timing verification? Mostly we'll check with respect to the clock timing constraints, with respect to the clock, and SOC verification, and also pre-silicon verification, post-silicon verification. Everyone clear?
Yes, ma'am.
Okay. Let me know everyone. You can ask your doubts, whatever the doubts you have. Sai, Krishna, Sunny, Sagar, Manoj, Aditi, Sweta, Ram, and Muralidhar. So whatever you have, Tarun, Vinita,
Hello.
Ranjit. Yeah, hello.
Yeah, hi Prashanti. So actually, I have a doubt. Like as you mentioned, right, pre-silicon verification as well as post-silicon verification, right? So generally, so post-silicon verification is also done by like front end, or like it's like DFT will, like you mentioned, right? Debug will be connected, like different IP blocks is connected via debug, and after that some tool, right? So this thing is also done by like this system Verilog as well as UVM
Yes.
we use.
Yes, we use system Verilog and UVM only, but post silicon means mostly it's after we call it as a like after manufacturing process. But before that, we will have the exact specification and the piece of code we do before, right? Based on that design, also we do the verification in post silicon because exact hardware will not be ready. Everything will be there in our server. We do the verification, we check all the constraints and get the 100% coverage, and then we do the exact hardware. First we'll just have one piece of hardware, with that we do the verification in post silicon.
Okay, so is there any change in the process? Let's say we suppose we write any test bench for particular design. The only difference is there, like in pre and post, like the silicon difference, right? Like the actual hardware we got.
In pre-silicon, I told, right, the debug units, in post-silicon, mostly we work under DFD. DFD in the sense designed for debug, DFD. Okay. So their separate hardware is there. DFD team have separate hardware because I told we connect the debug units using the cross trigger network. Suppose here there will be a processor, memory, controller, and some other IP something will be there, right? So here, whatever we are connecting here to here and here to here, these all will be connected to cross trigger network, and here there will be debug units. So this whole setup can be done in the post silicon. According to that team, we do the verification test cases, everything is different. Pre-silicon and post-silicon, everything is different. In pre-silicon, we don't have this type of hardware and also this type of setup. Majorly, we connect with the Wombat and to the computer. And here we'll, in the computer, I mean in the software, we will get all the data regarding to this hardware. So how we are connecting means by using the debug unit, debug streaming data will be there using the cross trigger network. So whole data will be connected to the software. So this thing is different. Pre-silicon is different, post-silicon is different, but in both we use C language, system Verilog and UVM.
Okay, so are we going to cover in this course like any pre-silicon as well as post-silicon examples, like how we can write test bench?
Yes.
Okay, sure. Thank you.
So when, in which case we use C language for verification and system Verilog UVM for verification in SOC level? Can anyone tell?
For pre-silicon, we will use mostly SVUVM, and for post-silicon, we'll go with the system C-based verification, C-based verification.
Why?
I mean, the complexity-wise, to verify the functionality more enhancingly, SV and UVM will be used in pre-silicon.
Okay.
Whereas in abstract level, at post-silicon level, we will use C language.
Okay. But in post-silicon also, everything, the design will be connected, right? Whatever we have designed using the hardware description language, those design only we are going to verify in the post-silicon also. Then why do we use C language?
The debugger units and all, if we want to use their for post-silicon verification, they will function on the C language basis, I think.
Okay. Do you have any idea about debug unit and all? Or you are just telling randomly?
No, I have idea about that.
Okay. But okay, whole design we use C language, like not only like okay, first complete from your side how you are telling your perspective. I mean, I don't tell like everything we do the using C language. Particular scenario.
Wherever DFT, wherever DFT components like JTAG protocol or some protocols are used, there we will try to interface with C language.
Okay.
Otherwise, we will proceed with SV and UVM approach on.
Okay, fine. So, okay. Suppose here is a SOC, system on chip. Mostly the processor, whenever the processor is, mostly processor will connect with all subsystem. Without connecting with the processor, we don't have any signal, right? So processor signal, obviously it will connect all the subsystems. So whenever the processor signal is there, because processor in the sense I already told that processor have n number of cores, nothing but we write the instruction set using the assembly language program. Only this processor is designed using the assembly language program, because by using the instructions, based on the instructions only, entire architecture will work, right? Remaining all hardware will work with the normal hardware description language. However, we design the digital logic design circuit, entire remaining all blocks are related to the hardware description language, except main processor, graphic processor, and if have digital signal processor, except the processor, remaining all of hardware description language. Okay, so that's why remaining all hardware we verify using UVM in industry. Whatever the whatever the core processor related test cases are there, only those test cases we verify using C language. Remaining entire SOC we verify using UVM only, not event system Verilog, we use mostly UVM. Okay, why? Because the processor to debug the data, the system Verilog is mostly written for hardware components, whatever the hardware components are there, we write mostly for that. But in C language, it is easy to debug any assembly language program or even normal high level language. If you write any high level language program, that would be easy to debug with a C language. That's why for processor, we use the C language, remaining entire chip, we use a UVM. Okay, clear everyone? That's why mostly in SOC verification, we write the C test cases. If you are applying for SOC verification role, C and C++ also required. But for freshers, we can't tell you can apply any of the role. It totally depends on how you work on the project in industry. Once you get into the industry, based on which project you are getting, maybe you will get SOC verification or IP level verification or any core related verification or CPU related verification. Anything you may get. Okay. Clear everyone till here?
One thing, Prasanti, here in you mentioned IP verification and RTL verification, two types. So RTL verification is a part of IP verification, right? I mean, RTL verification will be there, right? In either in the subsystem IP or
Actually, in IP also we will have the separate blocks. Suppose router project is there. Router is a IP. Suppose if you consider router is a IP, but inside router we will have a finite state mission, synchronizer will be there, FSM will be there, not FSM, FIFO memories will be there. So these RTL separately. Anyway, we will write whole test bench architecture. If you verify with separate RTL design, separate functionality, then we call it as a RTL verification.
Okay.
RTL also comes under IP only, but IP is all related to the particular functionality, whole block. Okay, clear everyone till here? Any doubts?
Yes, ma'am. I want to ask one thing. There is something like GPU and CPU verification. So may I know what is the difference in both?
See, GPU means it is designed only for graphic related. Why we are using graphic processor to improve the high quality, the picture quality, or mostly for graphic processor or more number of cores where we run the multiple applications task related to the video gaming. For that purpose, we have the high speed processor. Suppose if you do video editing or Photoshop in your normal laptop, if there is no graphic processor, if you work with your normal laptop, it doesn't go fast. That means the task will do very slowly and hanging issues will get. Why? Because normal processors will not sufficient to work with those high speed graphic things like video editing or Photoshop. Especially for that purpose, we have the graphic processor, which have more number of cores, work at a high speed video gaming purpose, like that, graphic purpose.
Okay, ma'am. So in this verification, what we use, like C++, C or SV or
Processor,
UV?
any processor, we use the C language only, C++.
Okay,
System
in GPU
Verilog also
also.
you can use, yes, System Verilog also you can use, but we need to convert again from System
Okay.
Verilog
In
C.
GPU and CPU, both we use C or
CPU.
C++.
Yes.
Okay.
Both are
Thank you.
instruction set only, but for graphic processor we use different type of instruction set. It's not open source. Mostly for normal processors we have the open source like a RISC processor or x86 processors. For graphic
Okay.
processor we have different coding style, although it is a instruction set, but it's a different coding style.
Okay. So RISC-V and all we can use there.
RISC-V is a normal processor, it's not graphic processor.
Okay.
Graphic
Okay.
processor in the sense is totally cores, number of cores. So how we design number of cores based on the instruction set only, right?
Okay.
Core
Okay.
in the sense. Yeah.
Okay. Thank you.
And next, what is the purpose of verification? So you already understood what is the purpose of verification, right? Mostly to detect the errors and debug the error and fix the error before the chip is fabricated. Okay. So mostly what are the key reasons for performing verification? Mostly to detect the error and debugging, avoiding the chip failures and preventing system failure after like without going to the fabrication. Before that only we need to check and debug, and reducing communication gaps and ensuring reliability. And next, how to verify a design. So first of all, you are going to learn system Verilog, right? So how we are going to verify a design? Whatever the design, we will start with a simple adder only. Adder, flip-flops, or registers, counters, or FSM, or memory, whatever. First consider the design which already verified in a Verilog HDL. Okay, I will suggest you everyone, whenever you are going to write a system Verilog program for any design, first of all, verify the design using Verilog HDL. Okay, once you get the output in Verilog, then move to the system Verilog because you are freshers, right? If you go with the directly system Verilog, obviously in the first time, you won't get the error. You won't get the output. You will be getting lot of errors. That time you may get confusion whether the error is getting from design or a test bench. Okay. So to avoid that, first of all, if you verify a design using Verilog test bench properly, so you will get 100% clarity. Okay, design is working clear. Okay. And then whatever the issues are getting from next time, it will be from system Verilog test bench only. Okay. So first of all, consider a design whatever and apply the input stimulus, get the output. And we need to check the referencer. Suppose in Verilog HDL, how whatever the issues are getting from apply the input stimulus, get the output. And we need to check the referencer. Suppose in Verilog HDL, how we check normally just whatever the output we got, we check with the manual calculations. Okay. But in system Verilog, by default, we write the program in scoreboard like golden reference logic. Okay. So with the referral value, we check the output. Okay. So if both are equal, then we can say our design is 100% correct. If both are not equal, our design is wrong. Okay. Next, how to verify a design. Evaluate the results. If not equal, compare both, and we need to whatever the design issues are getting, we need to check that issues and fix the issues. Next, what is mean by linear test bench in Verilog HDL? Till here, everyone clear how to verify the design?
Yes, ma'am.
Any doubts? Okay, just wait. I'll get back in 2 minutes. Okay, no doubts, huh? So what is mean by linear test bench using Verilog HDL? How can we write a test bench? We will check, and then we will discuss about system Verilog test bench architecture. Okay. how to write the different components we will discuss today. So for system Verilog, we use QuestaSim tool. Okay, QuestaSim and GVim. Anyway, from this weekend, we are going to start system protocols, right? In weekends, protocols. Saturday, Sunday, protocol. Okay. Actually, in protocol, we use system Verilog and UVM verification, but you no need to attend for system Verilog UVM verification. Okay. If you already have basic idea, you can attend, or else no. Just attend for theory wise. Okay. So that if you want to apply for internships or if you want to apply for jobs, it will be easy if you learn the protocols now itself. You can concentrate more into the programming, and parallelly you can work with the protocols also, because if you learn one time, it will not remember till next 4 or 5 months, right? You can practice from now itself. Okay, so from this week, Saturday, Sunday, you can join for the protocol sessions. That time I will explain the tool. Okay, how to install the QuestaSim tool and how to use the GVim. Okay. So how to write a linear test bench? Suppose there is a Verilog design. This design is related to the 16:1 multiplexer using 4:1 mux. Okay, how we can write the program for 16:1 mux using 4:1? You already know, I think. First of all, we need to design a 4:1 multiplexer. It have 4 number of inputs and 1 output and 2 selection lines. This copy we need to connect in 4:1 mux using 16:1 mux. Suppose 4 inputs will be there. Here 4 inputs, and 4. 16:1 mux. And here there will be 2 selection lines, and here there will be 2 selection lines. We need to design using Verilog HDL. Okay, so first of all, we design a 4:1 multiplexer. This is what the design code. So this is what simple, how we can write the multiplexer program very simply. Assign y equal to d of select, and we are taking the multiples, 4 copies, 5 copies, right? 5 number of mux are there, so we are taking 5 copies and make the connections. For this, how we are writing the test bench? First, in third line, we are writing the module, and fourth, fifth, sixth, declaring the inputs and outputs. You already know inputs must be declared with a range and outputs must be declared with a var data type, because we are using procedural assignment statements, right? So that's why. Next, interfacing the design and the test bench. Mux 16:1 is a design name, and DUT instance name DSY. Next, initial begin $monitor is a system task or simulator directive. We are writing the program. We are writing the printf statement here, just to print the statement, and D equal to some 16-bit binary value, and S equal to some values. Okay, dump on, dump off. Okay, so these all are related to the Verilog dump file, dump as to dump, to open the dump waveforms. Okay, so if you see in Verilog HDL, everything we are doing manually. D equal to some manual value, hard coded value. S equal to some hard coded value, like that. If there are 16 combinations, we need to give 16 number of inputs like this. Okay, so everything is a linear. and also time taken process. Suppose if it is a 32-bit data, we cannot assign 32-bit values, right? 2 power 32 number of scenarios we can't assign. So that time also it will be very toughest task, like time taken process. So these are the inputs and outputs you can check for the multiplexer. So to avoid this, we are using the random $random. Okay. So instead of assigning s equal to some value like that, we can directly put a $random. Even if we put $random, in most of the cases, controllability is not possible in a Verilog HDL, right? So to avoid all these limitations, we are using system Verilog test bench architecture. Okay. And also we cannot connect this module in a dynamic in nature. We cannot change these things in a runtime. But if you don't change in runtime, how many of you remember in the first last 3 demo sessions we discussed about the runtime? Did anyone remember? No? Okay, whenever we get some time, we will discuss that. So this is what the manual process using Verilog HDL. Okay, but these things we can avoid in the system Verilog. So how to write the system Verilog architecture? So however we write in Verilog, it's just a simple format, a very simple format. But in system Verilog, we need to follow the architecture. So I think everyone know this architecture, right? Can anyone explain? I think, have you gone through the 3 demo sessions? Then only you will get the clarity. Can anyone explain?
Yes, ma'am, I can try.
Yeah, please.
So, ma'am, there is a
What's your name?
ma'am, my name is Adarsh.
Adarsh. Okay. Yeah, please explain.
Yes, ma'am. So inside top we have test. Inside test we have environment, and this is dynamic in nature. So you have a generator, driver, monitor, scoreboard, and we use mailbox for transferring data from driver to generator and so on and so forth. And there is an interface between the DUT and the environment. So DUT is static in nature, and we have interface because interface converts uh, um, in from packet level to pin level. It does convert the packet level data to pin level data. And should I explain the functionality of each box?
Yes.
Like generator
Anyone?
generates the stimulus.
Can anyone explain other than Adarsh? Can anyone?
Yes, ma'am, I can try.
Okay.
Yeah, generator is responsible for generating the stimulus, which we will use for verification.
What's your name?
Sai Krishna, ma'am.
Okay.
Yeah. So generator will generate the stimulus which is required for the verification of the DUT. From there, through transaction, we will drive the data through the driver into the DUT. So the DUT will give the expected value, generated value to the monitor. So in the monitor, we will write the logic for comparing the data as well as golden values. And in the scoreboard, we will compare the actual data and the output data from the DUT, whether it's equal or not.
Okay. What is the use of mailbox?
So mailbox is used to like the stimulus which is used using the generator will be driven to the driver using the mailbox. It is used for inter-process communication.
Okay. Any other answers? Others, what is the use of environment tester, test bench top? Can anyone explain?
environment encapsulates these components, that generator, driver, monitor, scoreboard, and test actually encapsulate the whole environment, uh, and that and this environment can be used in different tests uh, to verify the DUT. And test bench top actually encapsulates the test.
Okay, fine. Okay, good. I will explain. So first of all, design DUT, design under test. We need to interface with our test. This is our test. Okay. In Verilog, whatever I shown now, the test same. Okay, but it is totally different here. How we are interconnecting our DUT to test using interface. Okay, interface means it's a block. We need to create one interface and interface. Within that, we will connect the signals. Okay, we will discuss clearly what is meant by interface, what are the limitations of interface, why do we use virtual interface in the next coming session. And coming to the generator. Generator is a class. Okay, all these four components are classes only. Generator is a class, driver is a class, monitor is a class, scoreboard is also a class. Okay, so within the generator, first of all, before that, see here, transaction. Transaction is also a class. Okay, what is meant by transaction here? In transaction, we will declare all inputs and outputs. All inputs and outputs we declare in the transaction. So, however, here we declare all inputs and outputs. Same in transaction also will declare. In interface also will declare. Mostly you will confuse between interface and transaction, but I will give you the clarity. Next, generator. Generator means whatever the inputs we declared here. In system Verilog, we don't create the hard-coded values. Okay, we create the random values, randomization. Okay, so in the generator, we create the random values. We do the randomization in the generator. Okay, so after doing randomization, what happened? Suppose address will get some random value assigned to the address. Data equal to some random value assigned to here. Okay, like that, a lot of values will be assigned to the inputs, different random data. Okay, that random data we are sending to the driver. Okay, actually here from these two we need to send directly to the DUT, but we cannot send directly to the DUT. Here we are using the driver. Okay, from the driver we send same address values, data values, input value, clock, reset, everything using the driver to DUT. All the control signals or bus signals, whatever the inputs are, we are sending from driver to DUT. Here we will have the packet level data. Packet level data means what? Everything we do the randomization in terms of packets, number of bits. So that packet level data will be converted to the pin level data. Pin level data in the sense in DUT, everything will be connected in terms of signals, in terms of pins. Okay, to the main functionality. So that's why we will call as a pin level activity, pin level data. Okay, so here how the data is getting from generator to driver? Via mailbox, right? Mailbox is a component here. It's not a class. Okay, just a component. We create the mailbox in a generator and a driver. Okay, and whatever the data we are randomizing here, we put the data into the mailbox and we get the data in the driver. Okay. So you may get the doubt why we are putting the data into the mailbox. Why can't we send directly the data from generator to driver, or same here, monitor to scoreboard? Can anyone tell why we are creating the mailbox here?
For synchronization purpose, like with the clock.
Okay. For synchronization with the clock. Without mailbox, can't we do synchronization?
There might be some delays in the stimulus.
Okay. Okay, suppose if generator is working at a high speed and driver is not working at the same frequency, both are working at a different frequency. Okay, and that too, generator may have 10 number of transactions or 20 number of transactions, suppose at this site, and driver may have driver also need to get the same number of transactions, right? Exactly those 20 number of transactions need to send to the DUT. Okay, suppose if generator is generating 20 number of transactions, but the driver can able to transfer only 10 number of transactions, that is not proper verification or proper transmitting transactions, right? That there will be a data lossage. Okay, so we cannot do like that. Whatever the initiator is sending the data at a consumer side or a target side, also we need to get the same data. Transmitter side, receiver side, both must be same. Okay, so if generator is sending fastly, like 20 number of transactions, it is sending fastly, but driver not able to get the data fastly, and it cannot send the data to the DUT in a same frequency. Okay, suppose if a driver is at the 10th transaction, driver is maybe at the 5th transaction only, still working with the 5th transaction only. Okay, and when generator is sending a 20th transaction, maybe driver by the time it is still working at 15th transaction only, slowly, because it time taken process to send to the DUT. It need to convert the packet level data to the pin level data. It takes some time. It should convert from the transaction to the DUT, right? So it is working slowly. So in that case, if both the frequencies are not matched, there will be a data loss, right? So whenever it is sending 20th transaction, it is still in 15th transaction only. At the same time, if other 5 transactions are not able to transmit at same time, those 5 transactions will be data loss, right? So to avoid that problem, here we are using mailbox concept. Mailbox is like a FIFO concept. FIFO is a temporary storage data, right? We store the data temporarily. Same here, mailbox also use it to store the data temporarily. Suppose generator is sending a 5 transactions. These 5 transactions, it will be stored in the mailbox, first, second, third, fourth, 5. So driver will get the data one by one. So whenever it is completed one, next second one, and next third one, and next fourth one. So based on it, based on its frequency or delay, it will be getting one by one transaction from the mailbox. So there will be no data loss. Okay, same way, driver is sending the data to the DUT. DUT will take that input signals and work with the functionality. After that, it should print the output, right? So to print the output also, here we have a lot of process in system Verilog. First, this DUT will send the data to the monitor. Monitor will get the data from DUT to the monitor. Okay, and then it will send to the scoreboard. In the scoreboard, we write the golden reference values. Golden reference values means what? Suppose in Verilog test bench, here is a Verilog test bench. If you want to verify your output and with these whether output is correct or wrong, how you will verify this output? This output, you need to check manually. Okay, whatever the functionality it is, you need to check manually whether it is correct or wrong. But in System Verilog, we generate the golden reference values in the scoreboard, and we write the expected value and actual value. If expected value, which is our manual calculation, actual value is the manual calculation, expected value is from the DUT. If both are equal, we write the logic like that. If both are equal, our output is correct. If both are not equal, our output is wrong. So that automatic logical value, like a golden reference values, we can check, we can generate in the scoreboard. Okay. So these all are 4 classes: generator, driver, monitor, and the scoreboard. So these 4 components we are connecting in the top level called environment. From the environment only we will run these 4 classes. This environment will be connected in the top level test, and test interfacing with the DUT will be connected in the top level test bench top. A top test bench top is the main where we connect the interface and the test. Okay, so whenever you are writing the System Verilog program, you need to follow these blocks. Okay, clear everyone? Now we will see how to write a program. Overall, just idea I will give. Suppose right side one is a design program. This program is related to the calculator. Okay, and not calculator only. So for the design, left side we write the program. Okay, suppose if you see here in PPT, first we need to create the generate block, not generator block. First of all, we need to create the interface. Whenever you are writing the program, follow the same flow. First create the interface. How we create the interface? Like this: calcif.sv file in EDA Playground. I will tell you installation process later. You can also use EDA Playground, but better practice in a tool only, because you will get the tool idea also. In industry, you need to work with the tools, right? So you will get that idea. But whenever you want to write quickly the program for quick access, you can use the EDA Playground. Okay. So interface block, this is how we write the interface. We write all the input and outputs here. I will explain later clearly. Clocking blocks, mod port, we write like this. Okay, after creating interface, we need to create the transaction class. Transaction, so calci_trans.sv. So transaction is also a class transaction. We need to declare all inputs and outputs, and we need to write the constraint. This code is like a project level. Don't think like it's very complex type of program. Don't worry. You will learn every concept from scratch onwards. Okay. So from day 1 onwards, whatever the concept you are learning, every concept is used in this whole test bench. Every concept is important. Okay. So by using all those concepts, mostly we write the program here. Okay. So this is how we create the transaction class. Just declare all the inputs and outputs variables and create the generator. Generator is also a class. So if you see here generator.sv, it's a class. So what we are creating here, transaction, because this transaction data only we need to do the randomization, and we need to send to the DUT, right? So that's why whatever the calci_trans class name is there here, calci_trans name, same we will create the instances here. Mailbox, we need to create the mailbox. Mailbox is not separate class, it's just a component. You just need to create like this. and it's a constructor to create the class and also task. So if you see here 18th line, trans.randomize. Here we are doing the randomization. In Verilog HDL, how we do the randomization? Just a $random. We put $random, right? But here we use the randomize method. Okay. And then now next driver. So if you see here, after doing randomization, 20th line, gen2dir.put. That means we are putting the data into the mailbox. After doing randomization, we are putting the data into the mailbox. Okay. Same here also. From the generator, we put the data into the mailbox, right? In the driver, we need to get the data from mailbox. Okay. Same we do in a driver. Go to the driver.sv. So here we created the class driver
Ma'am,
virtual interface.
yes, ma'am.
Yeah, tell.
I had a doubt in the task. Why we declared it as virtual task?
Where?
Yes, ma'am, this one.
Here virtual task is just for overriding purpose.
Overriding.
Yes. It's
Hmm.
mostly we use virtual task and virtual functions in system Verilog and UVM just for overriding purpose.
We could have used just task, static task.
You can also use static task. That's not a problem. But if you use virtual task, mostly in class based verification, everything is created in a dynamically, right? That's why we use a virtual.
Okay.
We will discuss more clearly virtual task, virtual function, and virtual class, abstract class is nothing but virtual class, right? So next, yeah, driver. So in driver, we create the mailbox and the class function constructor, and in main task, we are sending the transaction data. Left hand side one is the transaction data. Okay. Sorry, right hand side is the transaction data. Left hand side one is the DUT. Okay, connecting with the DRIF. That means virtual interface. And if you see here, 44 line, how we are getting whole data through the get method. Gen2dir. Gen2dir is a mailbox. Dot get. Okay, by using dot get, we are getting the data into the mailbox. That's it. Driver. Next to monitor. Monitor is also same as a driver, but right hand side we will connect a virtual interface. Left hand side transaction data. But in driver, right hand side a transaction data. Left hand side a virtual interface data. Okay. So if you see here 66th line. Same here also, put method. By using the put method, we are putting the data into the mailbox. From the scoreboard, we get the data from the mailbox. Next, scoreboard. Same scoreboard also same. Getting the data from the mailbox, 15th line. Next, comparison. Just here I have copied this whole design program to here, but mostly we write the comparison logic very simply. That's not required. So if you see here, if data RC, it's related to the actual data, and CP data from the output. If both are equal, that means whatever the data we got from the test bench and whatever the data we got from the design, if both are equal, data comparison is successful. Data is correct. Okay. If both are not equal, failed. Output is wrong. Comparison failed. Like the response. Here it's a 4-port calculator project. We have the data signals, response signals, command signals, tag signals, like that based on specification. So that's why we are checking with every response and also tag signals and the data signals. If both are equal, we get the comparison output. But this thing we cannot write in the Verilog. Verilog, we just write the manual calculation and directly we'll check that the output side. We don't have these things, right? So now we have created all these blocks. Transaction class created, generator, driver, monitor, scoreboard, everything created. Do you have any doubts still here? No doubts? Okay. Next, environment. In environment, what we have, this top level environment, generator, driver, monitor, scoreboard, transaction interface, all submodules are connected in the top level. So we include all the submodules here and create the class environment, and then just run all the subtasks from the environment. Create the all subtasks and run the subtasks from the environment. Okay. And then what is the top level module? Tester. In the tester, we run the environment. So include the environment here, first line. And in the environment, in the tester, 8th line, created the environment instance and calling the environment task from the tester. And what is the test bench top? This tester and interface both are connected in the test bench top. So this is what test bench top, test interface both are included here, and this is like main Verilog test bench. However, we connect main Verilog test bench like clock, generating the clock and instantiating the clock data, reset, and DUT interface and main DUT signals, same as a normal Verilog program. And $dump file test, main test is calling from here. Okay. So this is how I'm just giving the overview today, but this thing we need to design after all system Verilog concepts. Here I mentioned all system Verilog concepts, right? So once completed all these concepts, then you're ready to design that whole test bench. Okay. So you need to wait till 1 month, maybe 1 or 1.5 month, mostly 1.5 month. Okay, will take to complete all these components. I mean, concepts. Clear everyone till here? This is what today's session, and tomorrow also we'll have a session because yesterday we missed the session. So that's what today I covered, and tomorrow normally. And your schedule is Monday, Wednesday, and Tuesday, Thursday, Saturday, right? Okay. Okay. Any other doubts till here? Sai Krishna.
Madam?
Yeah, tell.
Madam, without agent we can write the test bench. Is it possible?
Without?
Agent class.
In system Verilog, we don't use agent. In UVM, we use agent.
Oh, okay.
In UVM particularly, we use the agent, but system Verilog, we have a concept, but we don't use.
Okay.
Okay. Any other doubts, others? So, okay, practice. I will share the recorded session. Okay. And I will share the assignment also. Assignments will start from the next session. Today, what assignment will be there? Nothing. So from data types, we'll start the assignments. And I will share the material also. Okay. Okay, then thank you all. Bye.